Across manufacturing, whether in high-volume continuous operations like petroleum refining or complex discrete environments like tire assembly or anything between, companies face a common challenge: the urgent need to digitize, optimize, and integrate AI without disrupting production or incurring upfront risk. Legacy infrastructure, siloed data, and high capex thresholds have long stalled transformation. The TAAIB vCPPS platform from TAAIB breaks this deadlock with a bold and differentiated solution: a fully modular, cloud-based virtual cyber physical production system, vCPPS, that enables any manufacturer to simulate, test, and validate AI-driven improvements before making physical changes. In this video, we will walk you through a bottling plant use case, where we will establish a dynamic plant-specific simulation environment, populated with the setup of digital twins of SKUs, process areas, machines, sensors, actuators, and PLCs. We will then show how these digital twins are later used to establish a vCPPS of the bottling plant. The vCPPS allow for the experience of the operational value of AI, digital twins, and simulation firsthand. This provides a risk-free, data-rich, and insight-driven transformation pathway that accelerates ROI, enhances agility, and bridges the gap between operational legacy and an AI-powered future. Simply put, we will show you that the TAAIB vCPPS platform doesn't just digitize manufacturing. It de-risks it, democratizes it, and delivers measurable value from day one, and we will show you how the TAAIB vCPPS platform puts a bottling plant on this journey.
Hello, in this video I'm going to create a simulation of the bottling plant. To do it, I will go to the Simulations tab and select Create a Simulation. I will enter the name of the simulation, define the production time for 10 days, speed multiplier 100, and total simulation production target as 10,000. Then next, we have to define the SKUs. In my case, I would like to have SKU1 as a sparkling water, 500 milliliters. The minimal simulation volume to be 5,000, daily minimum percentage 10, and time per SKU unit 10. Then selecting the SKU, we can define the processes. In this case, the first process is going to be bottle washing. Each process will consist of one machine. The machine for the bottle washing is going to be bottle washer with the capacity of 10, and it's going to have a temperature sensor, which I will assign to this machine, and the Celsius unit, location, input, and sensor mode single. It can measure the value from 40 to 90 with the randomness 2 and error rate, with the randomness 5 and error rate 2%. And the actuator, I would like it to be a water pump. I'm going to assign it to the machine with the units RPM. It should be logical based, and let's say the RPMs are from 0 to 500. Okay, so the first process area bottle washing is configured. Let's configure the next one. I'm going to call it bottle filling, and the machine will be liquid filler with the capacity per hour 10. And here it will have a lever sensor that I will assign to the machine. The unit, I would like to have it as a percentage. The start value is 0 and the end value is 100% with the randomness of 5 and error rate 2. And the actuator, I would like to have a filling valve assigned to the same machine. With the custom unit of non it should have a start value 0 and end value 1. Okay, we have two processes defined, and let's define the last process, which would be bottle capping. I will add a machine called a capper with 10 capacity per hour. I would like to have a presence sensor assigned to the machine. The start value of 0 and end value of 10. In this case, millimeters. With the randomness of 2 and error rate 5. And the actuator last will be a servo motor to put the cap on the bottle. I will assign it to the same machine. With the custom unit of millimeters, start value of 0 and end value of 100. Okay. Now let's define the new SKU. Should be SKU2 with the volume of 5000. So both SKUs are defined. In the next step, we can define the PLC. I would like to have one PLC controlling everything. Which is configured here. And next, we can review our settings and create the simulation. Here, we need to create a new vCPPS.
We have just walked you through the simulation module of the TAAIB vCPPS platform. It serves as the digital twin blueprint engine. It enables users to model complex manufacturing operations by defining process areas, machines, sensors, actuators, SKUs, and production logic in a no-code environment. This module transforms high-level production specifications into structured metadata that fully describes the intended behavior and layout of the factory, virtually and logically. Once the simulation is defined, the Smart Manufacturing module activates the virtual cyber-physical production system, vCPPS. It takes the simulation payload and deploys it into a live execution environment powered by MQTT, OPC UA, Node-RED, and InfluxDB. This module dynamically runs the virtual plant, executing the PLC logic, generating real-time sensor data, triggering actuator responses, and mimicking real-world operations with high fidelity. Therefore, let's now take you through this process visually.
Name it bottling plant simulation. You can see it's the new record at the very bottom. Let's load it. And here at the first screen, we can configure our SKUs. First, the SKU switching mode. There are two possibilities. It's either a total mode or the daily mode. I'm going to stay with the total mode, so it will switch when total target is reached. And the SKU settings for the minimum simulation volume and daily minimum simulation volume are coming from the previous settings, which can be also adjusted here now. I will go with I'm happy with the settings currently that I have here. Next, in the process areas, we can configure the machines, similar settings that we had in the previous configuration. But the other thing, if we are happy with them, there is no need of adjusting. But we have to set up the input and output sources. In this case, the bottle washer from the first bottle washing process area will have an input source as a process start, as there is nothing upstream of it. And the output destination, we would like to have a bin, but for the next process area, which is bottle filling. So bottle filling work in progress bin. Then at the bottle filling, the liquid filler will take parts from the bottle filling work in progress bin and output them the bin of the bottle capping, and the last machine will take the parts from the bottle capping bin and output them to the system process. And there's also a possibility of skipping the bins and having the flow directly from the machine to machine. It all depends on your specific requirements. Then next on this screen, we can configure the PLC logic rules to control the machines and whenever the parts are being processed. In this case, I will start with the first area of bottle washing, select the machine, and there's only one sensor. On the left hand side we can see the range. So in our case, if the value is higher than 50, in this case, for the same machine, the actuator water pump should be turned on. I will select the settings for the SKU1. The rest I'm happy with. I will add a rule. Next, the next process area is bottle filling. So we are filling the water in a bottle. There's a level sensor there with the range of 0 to 100. So in this case, we would like to fill the water whenever it's not 100%. So less than 100, and the process area the same. Actuator, our valve, in this case when it's lower, then we would like to turn it on. It will be for the same SKU, rest of the settings are okay. And the last process area, bottle capping, our capper machine, presence sensor, and the condition that we would like to have here is that when the value is greater than 2, In this case, we would like to have our electric motor turned on, which means that the bottle is present and we are going to insert the cap. It will be for the same SKU. And now I will repeat the settings but for the other SKU. It's possible to have a different settings depending on the SKU if there are different requirements.
You are seeing on screen how the TAAIB vCPPS platform is uniquely engineered to support the simultaneous production of multiple SKUs, each with distinct process flows, sensor-actuator configurations, and PLC logic. It dynamically maps each SKU to its respective digital twin representation, enabling granular control over sensor thresholds, actuator behaviors, and control sequences. This allows manufacturers to model real-world complexity, such as varying production parameters, changeovers, and logic routing, within a unified virtual environment, making SKU-specific automation, optimization, and simulation not only possible, but scalable.
All of the rules have been configured for all of the machines and all of the SKUs. So now we can move on to the next step to configure the protocol that is going to use. And in this case, I would like to stay with the OPC UA. And here we can review the steps and in case we would like to edit something, we can always go back. Let me commit and save vCPPS. I'm happy with the name, so I won't edit it. And now the simulation has started. We can already see that at the VIP bin counts, the process start is less than 100. It means that the part has started to be processed. The first part, it's because to simulate the cycle time of the machine, we are using the floating point number to simulate the correct production time. On the vCPPS information tab, we can see the number of cycles that have been already performed. And in this case, we have the SKU 1 active currently. So whenever the temperature is higher than the threshold, then we have defined, then the actuator will be turned on. And we will start working on the part which is being simulated by taking the partial part from the process start bin. Then it will be processed by the machine and the part will go to the next bin, and so on and so on. And at the very end, when the part is processed by all of the machines, it will end up in the process end bin, and also the total production for the respective SKU will increase.
As you have now seen and heard, the simulation has transitioned into the smart manufacturing module. Therefore, what we're now witnessing is the live operation of the virtual cyber physical production system, or vCPPS for this bottling plant. This is where the previously configured simulation blueprint comes alive. Every machine, sensor, actuator, and logic path are now actively running in a live environment, powered by MQTT, OPC UA, and Ethernet IP communication protocols. This isn't just a static playback. What you see here represents real-time virtual behavior of Industry 4.0 standard established digital twins of the operating plant. Every signal, whether a valve actuation or a bottle count sensor, is being generated dynamically based on the Asset Administration Shell, AAS structure defined during the simulation phase and the no-code PLC logic defined during the earlier setup of this vCPPS phase. This rich stream of synthetic yet highly realistic data mirrors how a physical factory would behave under similar configurations. As the bottling plant vCPPS moves into full operation, what's visible is the dynamic execution of the PLC logic paths working in parallel, each tied to specific machines, tasks, and control zones throughout the virtual facility. The system displays detailed tag activity as bottles move down the line, showcasing how each programmable logic controller, PLC, manages discrete stages of the process. From washing to filling and capping, we can see actuators triggering based on real-time sensor readings. For example, motors starting and stopping based on sensor input, or a cap placement actuator firing when a bottle enters position. Each of these interactions is timestamped, coordinated, and visualized as a digital signal trace, giving full transparency into how logic conditions are evaluated and executed. The platform supports not only synchronous logic execution, but also complex asynchronous flows such as error recovery, machine handshakes, and SKU-based switching. As different SKUs are simulated, whether sparkling water or energy drinks, the system would automatically adjust control parameters like fill volume, cap torque, and label alignment. These adaptations are all logic-driven and rendered in real time through tag updates, making visible the normally hidden world of industrial logic behavior. What's more, every tag's behavior, normal, edge case, or failure, is digitally logged and available for analysis. This visual traceability of logic execution allows manufacturers not only to validate control sequences, but also to stress test alternate logic paths, evaluate equipment interactions, and model scenarios like bottlenecks or machine faults. And because the TAAIB vCPPS platform is driven by structured data protocols like MQTT and OPCUA, this multi-PLC orchestration reflects what would occur in a physical plant with astonishing fidelity. And here's where the magic begins for AI. The data being generated through this virtual system is not just for show. It's structured, time-stamped, and perfectly clean, making it an ideal feed into downstream AI models. Every sensor activation, actuator response, and PLC state transition is captured with contextual metadata, such as SKU type, machine ID, shift timing, and simulated fault conditions. Take this bottling plant, for example, as different beverage types pass through the line, each with unique fill levels, bottle sizes, cap types, and labeling requirements. The vCPPS automatically adjusts machine behavior and control parameters. All of these adjustments are logged, meaning AI models can later analyze which configurations lead to micro delays, maintenance triggers, or energy spikes. Imagine training a predictive maintenance model to detect an impending kappa misalignment based on torque pattern deviations over time, or feeding SKU-wise throughput into a reinforcement learning model to optimize production scheduling and reduce downtime during changeovers. The beauty here is that the data is already simulation-derived and context-rich, eliminating the need for expensive sensor retrofits or risky historical data scraping. This is what makes the TAAIB vCPPS platform so unique. The simulation itself is not just a sandbox, it's a high-fidelity data generation engine purpose-built for AI acceleration. Notice how production metrics update in real time. Whether you're monitoring SKU-specific bottling rates, detecting downtime patterns, or measuring actuator response times, everything is synchronized to reflect real-world plant behavior, down to the millisecond. But what's transformative here is that all of this visibility comes without the operational risk associated with experimenting in a live production environment. In this bottling plant scenario, different beverage SKUs introduce variations in fill volume, labeling accuracy, and conveyor timing, testing how these differences affect line speed, bottleneck frequency, or mechanical stress would be prohibitively disruptive in a physical facility, not to mention risky to product quality and worker safety. However, within the TAAIB-vCPPS platform, all of these what-if scenarios can be simulated safely, repeatedly, and at scale. This eliminates the need for trial and error tuning on physical assets, reduces unplanned downtime, and enables proactive resolution of logic gaps or performance inefficiencies before they manifest in the field. Operators and engineers can test new PLC strategies, line balancing configurations, or machine upgrades in a virtual space, building confidence in changes before they go live. For manufacturers across sectors, whether discrete like automotive or electronics, or continuous like petrochemical or food processing, this risk-free simulation capability offers a powerful leap forward. It replaces intuition and manual guesswork with data-driven experimentation, shortening development cycles and enabling a more agile, digitally empowered production environment. For manufacturers, this presents a powerful opportunity for their AI and overall digitization journey. With the TAAIB-vCPPS platform, they can begin the AI journey at their own pace, what we call creep, walk, run. In the creep phase, the focus is on risk-free exploration and foundational AI enablement. By using the AI Agent add-on, users can instantly generate full PLC logic templates tailored to their own plant scenarios, all without needing coding skills, control logic expertise, or prior AI experience. These templates are not arbitrary. They're grounded in real-world machine behaviors and process dynamics modeled within the simulation. Returning to this bottling plant example, the AI agent generates logic that mirrors what actually plays out on the digital production line: coordinated actuator sequences, condition-based sensor triggers, and PLC routines optimized for SKU variability. Manufacturers can validate this logic within the vCPPS before anything is deployed in the physical world. This brings us back to the points made earlier. Manufacturers can test machine interactions, identify inefficiencies, and refine workflows, all before a single line of code is implemented in production. That's the essence of creep: learning, adapting, and building operational clarity in a safe, controlled digital twin environment. This staged approach dramatically lowers the barrier to AI adoption. Instead of confronting the complexity of legacy system integration or needing historical datasets up front, manufacturers can first simulate forward, creating value immediately while setting the stage for deeper AI modeling in the walk and run phases. Therefore, whether it's predictive maintenance, process optimization, or advanced planning, the foundation is already laid in the simulation and PLC logic structure created during the creep phase. As manufacturers progress to the walk and run phases, the TAAIB vCPPS platform evolves from a simulation tool into a full-fledged decision intelligence engine. In the walk phase, they begin layering complexity, simulating advanced logic paths, orchestrating multi-line or multi-SKU operations, and applying optimization strategies using synthetic performance feedback. For instance, in the bottling plant, users may experiment with buffer management, line speed variation, or SKU-driven actuator tuning to uncover process improvements. These logic adjustments can be benchmarked within the simulation environment, enabling rapid iteration without interrupting real operations. As they transition into the run phase, manufacturers unlock the ability to reverse integrate their own historical operational data, feeding it into the vCPPS to create what we call reality-infused digital twins. This allows simulation runs to be grounded not just in expected behavior, but in real-world historical conditions, failure patterns, and throughput trends. A bottling plant could, for example, use downtime logs and maintenance reports from the past year to simulate a more realistic shift schedule or stress test specific machine clusters under past fault conditions. At this point, they're no longer just simulating operations, they're predicting them. With structured simulation outputs and enriched historical context, AI models built within the TAAIB-vCPPS platform's AI module, powered by Azure Databricks, can forecast machine wear, optimize production schedules, or recommend control strategies tailored to evolving conditions. It's this convergence of simulation, generative AI, and operational intelligence that makes the TAAIB vCPPS platform not just a manufacturing tool, but a strategic AI accelerator for the entire industrial enterprise. We've intentionally made this video longer than most walkthroughs, not just to demonstrate the user interface or software mechanics, but to allow the practicality and depth of simulation to be fully appreciated. Although the TAAIB vCPPS platform allows users to set time multipliers that compress or accelerate the production cycle, we felt it was essential to show a full run where at least one SKU complete a full end product manufacturing journey, from raw material input to final packaged product. This immersive view helps convey the level of precision, realism, and process traceability embedded in the platform. Across continuous and discrete manufacturing sectors, this level of simulation fidelity holds consistent. Whether modeling the catalytic cracking process in a petrochemical refinery, handling SKU variations in a tire manufacturing line, or, as in this use case, orchestrating bottle filling and capping in a high-speed beverage facility, the TAAIB vCPPS platform adapts seamlessly. What unites these industries is not the process type, but the need for intelligent, structured, AI-ready data. And this platform delivers that without exposing manufacturers to operational risk or system instability. It abstracts away the technical complexity while retaining the physical authenticity required for real-world process evaluation. Each virtual actuator and sensor in the system behaves as it would in an actual plant. Actuators respond to logic conditions triggered in real time by programmable logic controllers, PLCs, while sensors emit feedback based on physics-informed digital twin models. This level of synchronized behavior enables users to conduct sophisticated diagnostics, identifying bottlenecks, validating PLC logic for SKU changeovers, or forecasting where cumulative system delays might degrade throughput. And because this is done in simulation with a created vCPPS, users can explore edge cases and failure conditions without ever pausing their real-world operations. Perhaps most importantly, the TAAIB vCPPS platform has been engineered for practicality and scalability. Manufacturers are not required to rip out legacy infrastructure, nor do they need to assemble massive historical datasets before deriving value. Instead, they start with simulation with vCPPS, safe, data-rich, and tailored to their process. From there, they generate production-grade PLC logic automatically using the AI Agent add-on. And when they're ready, they can transition seamlessly into full AI modeling using the Azure Databricks-powered AI module, taking advantage of secure serverless Azure architecture already embedded into the platform. This staged journey ensures that manufacturers can move forward on their terms, creep, walk, or run, without the cost or complexity of a traditional AI adoption and/or overhaul.
At the heart of the TAAIB vCPPS platform lies a modular architecture designed to guide manufacturers step by step through the journey from digital twin modeling to AI-driven optimization. Each module plays a specific role in this progression, allowing organizations to adopt digital transformation at their own pace, starting with structured simulations and culminating in intelligent, self-improving operations. What follows is an overview of how these 4 core modules work in concert to deliver a seamless, scalable, and practical AI enablement pathway. The simulation module of the TAAIB vCPPS platform serves as the starting point of the digital manufacturing journey. It provides a no-code environment where users define process areas, machine configurations, sensors, actuators, SKUs, and control logic. These inputs are transformed into structured metadata that forms a high-fidelity digital twin of the intended production system, laying the groundwork for downstream automation and analysis. Next, the AI Agent module leverages generative AI to convert this simulation metadata into detailed, ready-to-use PLC logic templates. With a single button click, users can generate logic documentation for multiple SKUs and machine types without writing a line of code. This ensures control logic is functionally aligned with the simulation blueprint and accelerates implementation by removing the need for traditional PLC programming expertise. The Smart Manufacturing module then brings the system to life by executing the Virtual Cyber Physical Production System, vCPPS. It deploys the simulation payload in a live, logic-driven environment using MQTT, OPCUA, Node-RED, and InfluxDB. The module runs real-time virtual operations, generating sensor readings, triggering actuator actions, and reflecting production behavior as it would occur in a real facility. Finally, the AI module, powered by Azure Databricks, transforms the structured data from the vCPPS into enterprise-grade intelligence. Manufacturers can simulate and train AI models for process optimization, predictive maintenance, quality control, and planning, using both real-time outputs and optionally injected historical data to test real-world scenarios in a controlled digital environment. Together, the simulation module, AI Agent module, Smart Manufacturing module, and AI module create a tightly integrated end-to-end pipeline, from digital design to real-time execution to intelligent optimization. This architecture allows manufacturers to start small and scale with confidence, eliminating integration risks, enabling faster validation cycles, and providing a structured path to operational AI without the burden of legacy systems or data dependencies.
This is what modern manufacturing enablement looks like. Data-rich, low-risk, AI-ready, and simulation-driven. The TAAIB, vCPPS platform, gives manufacturers the power to experiment, optimize, and scale before ever touching the factory floor. Therefore, before we move on to expanding on what the TAAIB vCPPS platform total value proposition is all about, let us bring your focus back to this bottle plant use case so you may appreciate more the extent of what is being demoed in this video.
Now we can see that the total production for SKU1 has increased to 1, which means that one part went through the whole cycle. In the production counts, we can also see the number of the parts being processed by respective machines and for the respective SKUs.
This bottling plant demonstration reveals more than just the power of a single use case. It exemplifies how the TAAIB vCPPS platform serves as a scalable, cross-industry foundation for digital transformation. While this scenario highlights a discrete production process with dynamic SKU handling, sensor inputs, actuator control, and real-time logic switching, the same modular architecture applies seamlessly to continuous manufacturing environments such as petrochemical refining, energy generation, food processing, and beyond.
While the four foundational modules, simulation, AI agent, smart manufacturing, and AI, form the core transformation pipeline, they are supported by additional platform components that strengthen industrial readiness. These include the Asset Administration Shell, AAS module, for Industry 4.0 compliance and semantic standardization, Grafana for 2D time series analytics and performance visualization, and immersive 3D modeling through Open Industry Project, OIP, which creates a virtualized visual twin of operational reality. For manufacturers, adopting the TAAIB vCPPS platform means more than just modernizing production. It's about unlocking a strategic edge. The platform bridges the gap between abstract AI concepts and real, measurable outcomes, helping leadership justify ROI without the need for historical data or risky infrastructure overhauls. It minimizes dependence on large in-house data science or software development teams by providing no-code tools and AI-powered agents that turn simulation blueprints into deployable logic in minutes. Furthermore, it preserves institutional knowledge by encoding operational logic into reusable digital templates, helping mitigate the effects of an aging or retiring workforce. Just as importantly, the platform is built on a robust, enterprise-grade technology stack powered by Microsoft Azure, Azure Databricks, and OpenAI. This ensures scalability, data integrity, and always-on reliability, critical for simulation and vCPPS runs that may extend for days, weeks, or even months to capture high-volume, high-variance operational scenarios. With Azure's secure infrastructure, OpenAI's generative intelligence, and Databricks' advanced analytics and modeling capabilities, manufacturers are assured that their digital and AI transformation efforts are not only practical, but protected, performant, and future-proof.
In essence, the TAAIB vCPPS platform doesn't just digitize the factory, it transforms it into a learning, evolving, intelligent system. By combining simulation, automation, AI, visualization, and interoperability with best-in-class cloud technology, it offers manufacturers a complete, actionable, and scalable pathway to Industry 4 success.
The path to smart manufacturing and AI-powered optimization doesn't need to be complex or risky. With the TAAIB-vCPPS platform, manufacturers can now embark on a structured, scalable transformation journey tailored to their unique readiness level and operational needs. Our 8-tier adoption model is purposefully designed to support the manufacturing industry's diverse digital maturity spectrum. Whether you're exploring simulation for the first time or looking to deploy advanced reinforcement learning models for multi-SKU production lines, there is a clearly defined entry point. Tier 0 enables AI agent functionality and offers a 30-day free trial for evaluation and proof of value. Tiers 1 to 3 guide manufacturers through simulation setup, virtual PLC logic generation, and live vCPPS execution. Tiers 4 to 5 enable AI extensibility with predictive modeling, iterative optimization, forecasting and planning, and automated AI-driven feedback loop into the created vCPPS. Tiers 6 to 7 support full customization, enterprise integration, and AI-powered digital twins of fully functional vCPPS aligned with and practically autonomously switchable with your real-world data and objectives. This phased approach enables manufacturers to creep, walk, run without being burdened by large upfront costs, data science staffing, or disruptive infrastructure changes. You start with high-fidelity simulation and no-code PLC logic, then scale toward AI adoption as internal alignment, ROI validation, and workforce confidence grow. And because the TAAIB-vCPPS platform is natively built on Microsoft Azure, your team benefits from secure, high availability cloud infrastructure, built-in scalability, and seamless access to OpenAI, Azure Databricks, and other Microsoft services. Our solution is fully integrated and available today in the Microsoft Azure Marketplace, allowing IT administrators, engineers, and leadership teams to deploy with confidence, using familiar procurement channels and Microsoft's trusted partner ecosystem. Now is the time to transition from disconnected tools and theoretical AI strategies to a single, unified platform that turns simulation into action, data into decisions, and vision into value. Get started today. Visit the Microsoft Azure Marketplace, explore the TAAIB-vCPPS platform tiers, and schedule a personalized walkthrough with our team. The future of manufacturing is no longer a promise, it's a platform, and it's ready for you.
Now we can see that the total production for SKU1 has increased to 2.